Is it visible? Now see here. In last session, we have discussed the slope and deflection of a cantilever when it is aware to point load at pre-end. Now you see here, this is your slope equation. This blue color is your slope equation. Okay, that we have derived from the bending moment equation. Okay, or deflection equation. Okay, after that we have calculated the maximum slope, and it is at the end of the beam. Okay, at pre-end. After that, from slope equation, we have taken the integration and we have derived deflection equation. Okay, this is your deflection equation here. This one is your deflection equation. Now after this deflection equation, we have calculated maximum deflection. Maximum deflection is at the free end, that is distance b to b dash. It is your maximum deflection that we have calculated from the deflection equation. Our concern in maximum cases, our concern is for maximum deflection and maximum slope. Okay, now after that, by using this same this theory, we have derived deflection and slope for a cantilever when it is away to point load at a position or at a distance a from the fixed support. This is a point load which is at a distance a from the fixed support. Okay, under this you will get the deflection, that is deflected curve up to here, and from here it is a straight line. Direct it is straight line. Okay, now from here to here it is a straight line, and you will get the curve shape up to this load. Okay, now in that case we have slope at this b1 or b, that is equal to the slope at c. That means slope at b and slope at c are same. Okay, that slope you have, or we have calculated from this w a square by 2ai, that is last uh, equation we have used as it is for this load at distance a. After that, deflection at b is wa cube divided by 3ai. Now by using that deflection and this slope, we have calculated the deflection at c, that is distance from c to c2, that is c2. It is yb plus c1 c2. Okay, that deflection we have derived here. This is deflection at free end, or it is a maximum deflection. It is wa cube divided by 3ai, that is a deflection at b, plus wa square divided by 2ai. It is a slope at b or slope at any point, that is b or c. Okay, into l minus a, that is the distance of load from the free end. Okay, here deflection at free end or maximum deflection is deflection at b plus deflection or slope at b into l minus a. Now if see here, if you remember these terms, these two equations, that is ib, that is ib for point load at free end and deflection for point load at free end, then there is no problem to write this equation. This is just a deflection. Okay, deflection when load is at free end. This is the slope when load is at free end. Okay, and this is the distance of load from the free end. Okay, only here L will be replaced by a. L will be replaced by a because load is at a distance a from the Okay. Now I will go to the next case. Slope and deflection of a cantilever subjected to uniform distributed load over whole span. Means this UDL of intensity is acting over a whole span. Now here L is the length of the cantilever and W is the intensity of the load. W is intensity of the load. Okay. Now under this situation we have to derive the deflection equation, slope equation, and we have to calculate the maximum slope and maximum deflection. Okay. Now same thing, same approach we have to use. That is m is equal to ei d2i by dx square. M is equal to ei d2i by dx square. Now for that purpose, we have to calculate the m. Now you see here, again you select the section at a distance x from the fixed end, monument at this location, monument at x section, it is, so here we will consider this load w into L minus x, and its line of action is at L minus x, means w is the intensity of the load and total load from x to b, it is w into L minus x, L minus x into line of action is at L minus x divided by 2. Okay, this is not new concept for you. It is a Benjamin at x. Now after that Benjamin, here if you simplify this, it becomes w into L minus x, L minus x, it becomes L minus x square by 2. Again here it is negative sign because it is going to bend the beam in downward direction. Okay, that is m is equal to minus w L minus x square by 2. Okay, now this is the Benjamin and this is the Benjamin at x. Okay, now you equate with the this equation, m is equal to ei d2i by dx square, m is equal to ei d2i by dx square. Now this becomes ei d2i by dx square is equal to minus w into L minus x square by 2. Okay, now this is your Benjamin equal to the ei d2i by dx square. Now integration of this equation, first integration, it is a slope. Okay, means integrate this equation for calculation of the slope, that is integrate bm equation. Okay, bending moment equation. Now when we integrate this equation, you see here, now this term I am not going to consider. You start from here, ei d2i by dx square, integration of d2i by dx square is dy by dx. Next integration of this is minus w by 2 is as it is, and integration of this is L minus x, it's a cube divided by 3. Okay, and into minus 1, sorry, divided by minus 1, therefore it becomes minus minus plus w into L minus x cube by 2 into 3. Okay, you will get this integration, that is ei dy by dx equal to w into L minus x cube divided by 2 into 3. Here this minus sign is cancelled with this minus sign. Okay, this minus sign is cancelled with this minus sign, that is minus 1. Okay, therefore you will get w into L minus x cube divided by 6 and plus constant of integration c1, now again you use the conditions, that is at free end, at fixed end, and dy by dx equal to 0. Okay, because that is fixed support. Fixed support means that cantilever is fixed at that location, fixed at this location. That means there is no any degree of freedom. That is, all degrees of freedom are 0. Okay, and your dy by dx is a slope, or it is a rotation angle, or it is a rotation about z axis. Okay, that is also 0, because it is firmly fixed. That means it is not moving in any direction. It is not rotating in any direction. Okay, therefore dy by dx is equal to 0 at fixed support, or at x is equal to 0, at x is equal to 0. Okay, now this is your condition. Now you put this condition, in this equation number 1. Now you see here, ei dy by dx equal to w into l minus x cube. X becomes 0, that is wl cube, okay, divided by 6 plus c1, and that equal to 0, that means if I write this equation, you can see here, I will if I write this equation here, this term is 0, now this l minus x, we are calculating that dy by dx at x is equal to 0. Therefore here this x is 0, it becomes w l cube divided by 6 is equal to c1, okay, is equal to c1, or now therefore you will get c1 equal to minus w l cube divided by 6. Okay, minus w l cube divided by 6. After that you put this value of c1 in this equation. Now your equation becomes ei dy by dx equal to w into l minus x cube, as it is, divided by 6 minus w l cube divided by 6. Okay, this is as it is. Okay, now this is your slope equation. Okay, slope equation. Now you see this slope equation, ei dy by dx and these terms. Now our concern is with respect to maximum slope. For maximum slope, your maximum slope is at x is equal to l, at x is equal to l, slope is maximum. Okay, now for calculation of the maximum slope, you put x is equal to l in this equation. Now you will get, you see here, when we put x is equal to l in this equation, it becomes w into l minus l, it is 0. Therefore this term becomes 0. Now when this term becomes 0, okay, remaining term is this one, that is minus wl cube divided by 6. Therefore your equation becomes ei dy by dx equal to the minus wl cube divided by 6, and now when I take this ei on this side, and this is a slope at b, when I take this ei on this side, it becomes dy by dx equal to the minus wl cube divided by 6 ei. It becomes okay, I will not write again. This becomes wl cube divided by 6 ei. Okay, now dy by dx at b, what I will do, I will write here as dy by dx at b is slope at b, okay, slope at b, or it is this ib. Okay, ib. Now ib becomes Here this equation ib becomes, here I will take ib equal to minus WL cube divided by 6EI, minus WL cube divided by 6EI, IB equal to the slope at B. It is your IB. Okay. Now it becomes minus WL cube divided by 6EI, 6EI. Now see here, it is a slope. Now I will remove the negative sign and I will write downward slope. Therefore, maximum downward slope is IB equal to the WL cube divided by 6EI. Okay. Now this is the equation for maximum slope when your beam is subjected to uniform distributed load over whole span. You can see here, this is the equation IB equal to the WL cube divided by 6EI. This is also one important equation, or it is one major equation. Okay. Now we have calculated the slope equation as well as maximum slope. Now you have this is a slope equation. Okay, and this is the maximum slope. Okay, now these two things are required for deflection. Now after calculation of the maximum slope in the cantilever, now we will go for the deflection equation and then we will calculate the maximum deflection. Okay, now see here, now you know the deflection is the double integration of the moment or it is a integration of the slope equation. Therefore I will integrate this equation. Now see here, when we integrate this equation, left side EI is a constant term, it is as it is. Integration of dy by dx is y. Next, integration of this term w is as it is, L minus x cube. Integration of L minus x cube is L minus x raised to 4. Okay, L minus x raised to 4 divided by 4. Okay, now here this term becomes negative because there is a minus x inside the bracket. Okay, that minus sign will make this term negative. Okay, next second term is WL cube by 6 and its integration is WL cube by 6 into x. Okay, now plus it is a constant of integration. So here just for calculation of the deflection equation, you integrate the slope equation. And that integration is also very simple. Okay, slope equation, and that is equation number 2. Okay, equation number 2 that you have to integrate, and integration of this equation number 2 is this equation number 4, and it is your deflection equation. Before going to deflection, exact deflection equation, we have to calculate the constant of integration. Now for constant of integration, again what we have to do, at this condition, you see here, at fixed end, again there is no deflection, or y is equal to 0. At x is equal to 0. That means at A you have y is equal to 0. Now you put this term in this equation. Now you see here, when you put x is equal to 0 in this equation, your right hand side will be 0. I will put here, this term is 0. Sorry, left hand side is 0. Next one 0. Next one. Now here x is equal to 0 means WL raised to 4 divided by 24. Now here WL cube x is there. Therefore this term is 0. Okay, this term is 0. So we'll get this C. If you solve this equation, you will get the C2 equal to WL raised to 4 divided by 24. C2 is equal to WL raised to 4 divided by 24. Now after that you put this value of C2 in the equation number 4. Now when we put this value of C2 in the equation number 4, what you will get? You see here first term is as it is, second term is also as it is, and last term C2 it will be replaced by this term, that is WL raised to 4 divided by 24. Okay. Now this is your deflection equation. This equation number 5 is your deflection equation. Now I will write here. This one is deflection equation. Okay. Deflection equation. Now after finding the deflection equation, you have to find the maximum deflection. For maximum deflection, what you have to do? You will get the maximum deflection at free end, y is equal to maximum deflection, or it is y b, okay, and this is at x is equal to L, okay, at pre and y is equal to y max, or it is yb, okay, yb, and that value you will get at x is equal to L, okay. Therefore see here, for getting maximum deflection, you put the x is equal to L in your deflection equation. Now when we put x is equal to L in this equation, you see here this equation becomes here eiy, and it is yb, we can say. Here this term becomes 0 because L minus L, we are calculating the deflection at L. Therefore this first term becomes L minus x, or L minus L, it is equal to 0, okay. Now this term becomes, here you have to replace the x by L, so you will get WL raised to 4, WL raised to 4 divided by 6, okay. Next, last term is as it is, so if you add these two terms, it is 24 into 6, 24 WL raised to 4 divided by 6, and 6 WL raised to 4 divided by 24, or when we add these two terms, you will get the WL raised to 4 by 8. You can do this addition yourself also. It is not complicated thing, it is simple thing. Now it becomes WL raised to 4 divided by 8. Now when we take this ei on this side, it becomes y is equal to minus WL raised to 4 divided by 8 ei, minus WL raised to 4 divided by 8 ei. Now see here, it is just a distance, therefore that is a downward deflection. This is a downward distance, so I can write yb is equal to plus WL raised to 4 divided by 8 ei, okay, and that is a positive when we take in downward direction, okay. Have you got this? Now this is a deflection equation for cantilever severe to uniform distributed load over the whole span, okay. Now it is downward, okay, in when we apply the load in downward direction. This is a downward slope, this is a downward deflection, okay. Now here it is your maximum deflection, okay. It is your maximum deflection. Now after deriving this equation is also very important, same to the last case. Now we will go to the next case. In between that, if you have doubt, you can ask me. Now next case, slope and deflection of a cantilever subjected to uniform distributed load over a distance a from the fixed end. over a distance a from the fixed end. Means here this is a cantilever, this is a cantilever, and this cantilever is subject to uniform distributed load, and that distributed load is only for distance or for a length a from the fixed support. Okay, from fixed support. Now same to the point load we are treating this one. See here, if you consider the deflection of this, you will get curve up to here only, and after that it is straight line. Okay, after that it is straight line. Means here you up to here you will get the deflated curve, and that deflated curve just just you will get the straight line because of that deflated curve from here to here. That means deflated curve is up to here, means your slope is changing up to here, and from here to here that slope is same. Okay, slope is same. That means end is end of that beam at this location, it is just extended up to here. Okay, do you agree with this? Now when we consider the this a distance as a pre-end, you will get the deflection at a, deflection at a, yb equal to the minus w a raised to 4 divided by ati. It is same to the last case. You can see it. This one, this one. It is your deflection equation, yb is equal to w a raised to 4 divided by ati. In this case, your distance is a, therefore it becomes minus w a raised to 4 divided by ati. Now slope at b, slope at b, slope at b, it is also same to last case. It is wl cube, l will be replaced by a, it is minus wl cube. Okay, minus wl cube divided by 6ei, that is minus w a cube divided by 6ei, minus w a cube divided by 6ei. Already I have told you slope at b equal to the slope at c, not necessary to calculate the slope at c. Okay, this same line is inclined from here to here, that is a straight line, and that line is tangent at b to that deflated curve. Okay, because that same line is extended here. Okay, now, and that is your maximum slope. Now our concern is what is the maximum deflection, what is maximum deflection. Now maximum deflection you will get at the c, at the c, therefore we have to calculate the deflection at c. Now for calculation of the deflection at c, see here this is a straight line. Now what I will do, I will draw the horizontal line from b to this vertical line cc2. Okay, that means if I have point here, I have point here b1, and b1 to c1, b1 to c1 is a horizontal line, horizontal line. Okay, or now if we draw the horizontal line, and if you consider this as a deflection at b, that is bb1 is a deflection at b, that is your w a raised to 4 divided by ati. Now this becomes cc1, it is same to the bb1, and that is equal to the deflection at b, and that is equal to the minus w a raised to 4 divided by ati, this equation. Okay, now next one I will consider this triangle, that is b1 c1 c2. We need to calculate c1 c2 distance. For c1 c2 we will consider this triangle, that is b1 c1 c2. When we consider b1 c1 c2 triangle, c1 c2 triangle, now see here this angle is a slope at b and it is ib, suppose. Okay, then c2 c1, here your tan theta, theta or tan ib, it is c1 c2 divided by this b1 c1, therefore c2 c1 or c1 c2, it is equal to the b1 c1 into tan ib. Now b1 c1, if you measure this distance from here to here, if this is a distance, then this distance is b to c, it is l minus a, or b1 to c1, it is l minus a. Therefore b1 c1 is l minus a, and tan ib is equal to the ib. Okay, for small angle, for small slope, I can write tan ib here, tan ib equal to IB for small angle. Okay. Therefore, this tan IB is replaced by IB only, and B1 C1 is L minus A into IB. Now you will get the C2 C1. It is equal to the minus L minus A W A cube divided by 6 AI. Now next one. Now if you calculate the deflection at C is CC1 plus C1C2. Here YC is equal to CC1 plus C1C2. It is equal to the WA raised to 4 divided by 8 EI minus L minus A WA cube divided by 6 EI. Now CC1 is this one you see here, CC1, and C1C2 is this one. Okay, C1C2 is this one. Now this is the equation for the maximum slope when cantilever is away to UDL for a distance A. Okay, it is same to the point load applied at a distance A from the fixed support. Okay, CC1 plus C1C2. Okay, WA raised to 4 divided by 8 EI minus L minus A WA cube divided by 6 EI. Okay, now you see here, if you observe this term, this is the deflection at B, and this one is slope at B. Okay, therefore we can write this equation. Deflection at pre-end or maximum deflection is the deflection at a point up to which load is applied, that is UDL is applied, plus distance of this P point or distance of the point up to the UDL is applied from the pre-end, that is L minus A, into slope at the point B, or slope at a point up to which load is applied. Okay. Now this is the second case. Okay. Now one more case is there. I will cover that case also here. If you are doubt in this case, you can ask me.
Sir, the tan IB is equal to IB equation आहे ते जरा explain करा की आणि
tan IB is equal to IB. Why we are taking this one? See here, if you consider this CC2, it is here. Maximum deflection is not allowed. If we get the maximum deflection, that means the value of the deflection is very high. Then that is considered as a failure of the component. Okay. See here, if you observe anything, that means here on crankshaft there is a flywheel. Now weight of the flywheel is very high. Am I right? Now
yes sir,
if that is a one load on the crankshaft, am I right? If your crankshaft deflection is very high, then we have to consider that as a failure of the crankshaft. Am I right? Okay. If it is
okay sir.
Okay. Therefore your deflection is in the fractions of millimeter. It is very small in actual components. In numericals we may get more value, but in actual components, this YC or this C2, that deflection is very small. Okay. Or now if this deflection is very small, that means this C2 point is very close to C1. Am I right? Means this triangle is like this. You see here, this triangle. Okay, we agree with this. Now
Yes sir.
when we take this point very close to here, then if we write the tan angle for that, tan IB equal to the C1 C2 divided by this distance. See here, for zero tan when tan 0 is 0. Okay, if zero angle is there, then tan is also 0, and this angle is near to 0. Am I right? If very small
Yes, sir.
angle means it is near to 0. Therefore we can consider tan IB equal to the IB. Okay.
Okay sir.
IB equal to IB. Therefore when we consider tan IB equal to IB, I can write this equation L minus A into IB, or C2 C1 equal to L minus A into this one. See here, in mechanics of material, or in this structural mechanics, high deformation is not allowed. if you get the high deformation or high deflection, then it becomes plastic deformation. That is not acceptable, and these theories are not acceptable for plastic deformations. Plastic deformation theories are very different from that. Okay, in whole content, our assumption is deformation is very small. Okay.
Okay, sir. Okay.
Okay. Now here only 3 minutes are remaining. Uh, Again, if you have doubt, you can ask me. We have 3 minutes. Uh, Next, one more case is there. Okay, and that may not be finished in 3 minutes. So I will cover that in next session, tomorrow session. Okay. If you have doubt, you can ask me. Otherwise, I will stop the meeting. In any case, and one more thing, you have to remember all these equations. You see here, this equation, this equation, this equation, this, and also derivations also you have to remember. Okay, the derivations are also you have to remember. Okay, now I will stop here.